I will now pass the floor to two colleagues of Maria that we had the chance to listen to before. And I'm calling Audrey Darnaude and Rigers Bakiu. I hope I'm pronouncing well. And they are, like Maria, from the Cost Action Sea Unicorn project. Audrey has over 20 years experience in marine ecology. She has described the connectivity patterns and life strategies of varied marine species. And she's, among other activities, as I understood, she's a very busy woman. She's chairing the Cost Action, unifying approaches to marine connectivity for improved resource management of the sea. So Audrey will explain us how MFC is measured and why it matters. And on his side, Rigers is an associate professor at the Department of Aquaculture and Fisheries at the University of Tirana, Agricultural University of Tirana in Albania. And there he is also the head of the fisheries, of the department. I again invite you to check in detail the impressive CVs of these two people. And I will just end up congratulating you, Rigers, because you were designed to be the most successful young scientist in 2016 in your country. So congratulations for this. Now we will listen first to Audrey, and then we will listen to Rigers, if it's okay with you, and then we will take questions and open the conversation after your presentations. So Audrey, the floor is yours.
Okay, so I'm going to try to share my screen. Okay, it's fine. So yes, I'm going to be honest with you in this part of the presentation. And so what I wanted to talk about is are the challenges in marine functional connectivity data production. And I want to take you with us in this field to show you how difficult it is to gather this information and how diverse the field is, and so the information that we gather. So first of all, I want to tell you a little bit more about how marine functional connectivity data is obtained. And as probably some of you already know, it's not an easy task because marine functional connectivity knowledge is difficult to gather. First, because access to the marine environment is limited, and also because the movement at sea occurs in 3 dimensions, and you have at the same physical spatial place the pelagos and the benthos that can have separate lives, and so it complicates the things, although there are interactions between the two. Another reason why it's difficult is because marine population sizes are large and very few organisms remain sedentary over their entire lifespan. And the third reason why it's difficult to measure is because many marine organisms disperse over substantial distances, and there is no real clear relationship between species life history traits like size and their dispersal potential. And so as a result of that, a wide diversity of methods and tools from varied disciplines have been developed to predict, reconstruct, or directly track individuals' movements, among population or habitats. Okay, doesn't work. Okay, for some reason my screen is frozen. Sorry. Oh no, it's fine. Okay, so I'm going to present you these different techniques, and mainly the main ones. And the first one that comes to mind when you think about describing animal movement, and it's one Maria already talked about, is animal tagging and biologging. And so for this, we have a set of tags. So you have acoustic. God, it's not my presentation. God, sorry, I will just have to change that. It's not the final presentation. Can't believe it.
There's a naughty bug to all of the sea unicorn
God,
people.
I'm so sorry, guys.
No problem, it's okay. You can be patient.
No, but I think I might have crashed it. Sorry.
Take your time, Audrey, no problem.
Yeah, it's going to be
5
fine.
minutes, breathe,
I'm
we're
just
here
going
and we
to
want to
open
listen
it
to you.
again, but God, because I copied Maria's presentation just in case on top of this one, and I think I crushed mine, which is okay. No.
Is there anything you sent us that we can
I sent it
use?
yesterday evening.
Yes.
I sent it to, yeah, sorry.
No, I received it, but it's the same slide that I see now from the screen you're sharing too.
No, there was an animation in it. Sorry, I'm just going to take 5 minutes just in case, because I've changed a lot of things yesterday. I'm so sorry, guys.
Sorry, Audrey, I can do screen sharing because I see that I have
you have something more complete. You have the last one I sent yesterday evening.
Yes.
Okay, thanks.
You're welcome.
I'll just.
So let's just wait for Igor to start sharing his screen.
I'm just going to try something just in case.
This?
Yes, please.
Okay.
Oh, sorry. Okay, so can you go back to techniques?
Yes. Is this?
Yeah.
Okay.
Okay.
Please.
Okay, fine. Thank you very much. Sorry. So I will just tell you when you change it. So sorry. So yes, the first technique that comes to mind is the use of tags and biologging. So you have a lot of different tags. And here you have an example. So you have acoustic tags, but you also have satellite and pop-up tags. And so if you can click enter. So using all these tags, you can get detailed information about individual migratory range and also the detailed movement, as you can see here on the screen for a tuna. So this tuna was tagged in Ireland, and you can see its detailed movement during the year and also its range of movement. Another thing that tags do is that they can be biologging devices. So lots of the tags that I've presented are biologging devices. And in fact, they allow to have information about the environmental condition experienced by the organism in terms of temperature, salinity, or oxygen, and it gives an idea of the drivers of connectivity. So obviously, all these tags give valuable information for a wide range of animals, from birds to whales and to fish, for example. But the problem is that they are not applicable for, can you go back, please? Not applicable for all taxa. They work only on large-sized animals, and they give only partial information on the lifetime movement of these animals because of a limitation in battery life. Can you go to the next one, please? So to round this problem, people have started using natural geochemical tags, which is looking at the composition of varied body parts. So sometimes soft tissues like muscle, but most of the work in this area use hard parts that have seasonal layers, and they have seasonal growth. And so you can go back looking at the lifetime composition of the body part. You can go back and have an idea of the lifetime habitats that have been experienced by the animals. Can you enter, please? Click enter. Yeah. And so it's the example I've shown here with the profile along an otolith. It's in a lake trout. And as you can see at the beginning, the strontium concentration, which is a proxy of salinity, is very low. And at some point, the fish reach sexual maturity at age corresponding to the annuli. And then it starts to have migratory patterns. And so it gives information about not only the successive habitats of life, so the nursery ones, the feeding ones, and the spawning ones, but also on the population or stock isolation or mixing degree, and also can give an information about the environmental record, so the drivers of connectivity. The problem again is that it's mostly limited to relatively large-sized animals, often with skeletons, because we use vertebrae, we use otoliths, scales, tooth, feathers, and sometimes statoliths for squid. But we cannot deploy it on microbes or tiny animals. And it also requires that the habitats and the regions that we want to discriminate differ in the environmental condition, otherwise the record is the same. Can you go to the next slide, please? Okay, so the the third tool and discipline that we use to describe marine functional connectivity is the use of genetical tags. So the advantage is that here we can apply it for all kinds of animals because they all have DNA. And looking at population genetics and parentage analysis allows to have an idea of the size and structure of metapopulations or populations, the degree of isolation of populations, and also an idea about the dispersal of these animals or vegetals, which means migration plus reproduction. So here, the second techniques that we have in terms of genetics is the use of environmental DNA. And as you probably know, we've started a few years ago barcoding life, and we now have a lot of code, genetical code for a very wide diversity of marine species. And looking at these by sampling water or sediment, we can have an idea of the species where they are in different habitats, and it gives an idea of the geographical range, but also the diversity of habitats where they can live. And so if you click enter, but again, there is another problem. So the problem is that it gives limited information on the lifetime habitat use, and also it doesn't allow for, in terms of population genetics, it doesn't allow to identify the key habitats where organisms feed but do not breed. So it's a limitation. And so to keep getting more information about marine functional connectivity, people have started trying to predict it. And the first type of model that they have developed is biophysical models that are based on ocean currents and behavior. And it works again for a very wide range of taxa, but because it's based on the current, it doesn't work for birds. And it's an example here that you have. It gives a, so here you have an example of what happens in the Indo-Pacific, and it gives the probability of dispersal through the year. And so you can get this kind of information for most aquatic species. So you have an idea of larval dispersal, at least for these species, when they have a larval phase. And the advantage is that it gives an idea of dispersal for small or inert sessile organisms, including microbes, phyto and zooplankton, also jellyfish. Can you click on enter, please? And the problem with this technique is that it's only predictions, and it's limited to aquatic organisms because it's based on currents, and it gives only partial information on the lifetime movement for large migratory species like tuna or sharks, but also for the animals like whales or sharks that don't have a larval stage. It doesn't. Next one, please. And so the last tool that we have is niche modeling. It works for everybody, so it's the most universal one. And what we do is that we use species distribution models. And here you have an example from the projections that you can make between current climate condition and projections for 2100 under two different climate change scenarios, LCP 2.6 and LCP 8.5, using two different approaches of modeling. And it gives an idea of where species are going to be lost and where they are going to increase and which one are supposed to be affected. So it gives an idea of present and future possible distribution of species, also the possible changes in community composition across habitats. But the problem, is that you have no information on the intensity of the flow of organism, and it's only prediction. So it only identifies habitats among which connectivity is or will be possible, but we're not sure it's going to be effective. So this brings us to what is needed to improve marine functional connectivity knowledge. And at the moment, we have three main challenges for this. So the first one is to gather operational marine functional connectivity data for protecting marine biodiversity. And before we can do this, important knowledge gaps on marine functional connectivity needs to be filled. For example, self-recruitment and life history diversity could both be far more important than we thought so far. And they are not really described at the moment, and their ecological or evolutionary consequences are consistently overlooked in marine management. So that's a big problem. The second challenge is to produce adequate MFC and associated knowledge for preserving ecosystem services. And of course, this is tricky because this requires to link species geographic distributions across life stages to ecosystem function. We already mentioned that earlier. And we are very far from it. Variations in biodiversity are just starting to be integrated into the models that predict energy and material fluxes within and across marine ecosystems. And on top of that, most models consider dispersal as the only type of organismal flow when you have many other movements like annual migrations that can connect ecosystem and contribute to spatial flow and energy to the flow of energy and materials. And the third challenge is to understand MFC drivers and forecast its evolution in the face of global change. And that's a big one, because to do it, we need to identify the past and present drivers of marine functional connectivity. And this involves complex interaction between abiotic and biotic parameters. And also because model parameterization for this requires high quality and relevant MFC data, but also it requires to link MFC metrics with physiological and biological requirements across species and life stage, and this is yet to be done. Next one. So that was the main challenge in theory, but we also have a big problem to get a comprehensive image of connectivity at the community or ecosystem level. For this, we need the varied techniques and disciplines that study MFC to be unified, because they differ in their assumption and in the spatial and temporal or sometimes taxonomic scales at which they produce the knowledge. And so to get a full pictures of marine functional connectivity across taxa, we need to unify and integrate these techniques under a common framework. And when doing this, we will need to build on the practice and needs of community ecosystem or ecosystem modelers. So the descriptor we produce of species lifetime movements are usable and can be fed into projection models. But also we need to build on the practice and needs of marine stakeholders. So the research and data we produce allow to actually address societal issues. Next. So this brings me to the cost action Sea Unicorn. Next, please. So it stands for Unifying Approach to Marine Connectivity for Improved Resource Management for the Seas. And it has started at the end of 2020, and it will last until the end of 2024. So for those who don't know what a cost action is, COST stands for European Cooperation in Science and Technology, and cost actions, they provide networking opportunities for researchers and innovators in order to strengthen Europe's capacity to address scientific, technological, and societal challenges. So cost action is not a research and innovation project, and it's not a fixed consortium. And I'm saying that because it can evolve all the time during the course of the action. So if you want to join and you belong to one of the cost country or one of the country that is already in our network, don't hesitate to contact us, because you can join at any time. So usually, can you just go back, please? So usually the cost action, the way it functions is that you have a network based on trying to harmonize balance between geography, career development, and gender balance. We follow a memorandum of understanding that has been signed at the moment by 35 countries, mostly in Europe, but you also have Morocco, Algeria, and Tunisia. So I've seen that we have partners here, so you can join us if you want. It lasts for 4 years, a minimum of 7 countries. And what is interesting is that it combines both research coordination and capacity building objectives. So it's not only about advancing science. Can you go to the next one, please? So cost activities, the idea is to strengthen Europe's capacity to address scientific, technological, and societal challenges. So for this, we are going to organize a lot of meetings, conceptual thinking workshops, technical workshops to advance science. We're also going to organize conferences to disseminate our outcomes. We're also going to have some training school, and this one is one of the first we contribute to provide training on the subject. And the last thing that we're going to do in the frame of the action is to have short-term scientific mission, which are scientific exchange visits between participants to foster collaboration, but also to train new early career scientists to new tools and new techniques. Next, please. So regarding the objective and structure of the network, the main aim of Sea Unicorns is to advance knowledge and unifying concepts and approaches in the emerging field of marine functional connectivity research. so it can contribute to the sustainable management of our ocean. And for this, we first intend to bring together the diverse types of marine functional connectivity scientists in order to identify knowledge gaps, but also devise common approaches to marine functional connectivity. We also want
Audrey,
to...
I'm sorry to step in. I would say you have 3-4 minutes left, because then...
I'm almost finished.
Okay.
We are going to promote their interaction with connectivity and ecosystem modelers to allow MFC data used for identifying priorities for marine conservation. And then we're going to strengthen the links with between scientists and marine stakeholders to promote the use of marine functional connectivity knowledge for decision taking in marine management and policy. Next. So the main task, the first one is to synthesize existing knowledge on marine functional connectivity and its drivers, to highlight where coordinated efforts would produce most significant advances. The second one will be to harmonize MFC research and promote data integration across disciplines to address theoretical or technical limitation, and also to build a universal framework allowing data integration. Then we're going to bridge gaps between marine functional connectivity and complementary research discipline to try to produce MFC data that can be combined with species functional role. Here is the one that gather your interest today. It's to bridge gap between MFC scientists, policymakers, managers, and end users to try to optimize the format and quality of MFC data for decision making, and also catalyze the implementation of MFC research-based policies. And the fifth one is to disseminate MFC knowledge to a wide audience to promote global awareness on MFC ecological and economic importance. Next, please. And so to finish with this, it's the last one, then Riggers is talking.
Okay, so I see people are leaving, so I just would like not to miss the opportunity. Yeah.
I'm sorry, yeah, we had a technical problem. So yeah, as you can see, CUNICOR is positioned at the Science-Policy-Society interface. Next, please, Riggers. And so we have 4 working groups. Working group 1, which is in charge of marine functional connectivity knowledge improvement. Working group 2 and working group 3, which are in charge of marine functional connectivity knowledge integration, respectively, with modelers for working group 2 and with stakeholders for working group 3. And working group 4, which is in charge of marine functional connectivity knowledge dissemination. And the next, so the 4 working groups will work in parallel during the whole course of the action, but many interactions are planned among them, and Riggers is going to present you what we're going to do in working group 3. Sorry about this.
Thanks a lot.